Hello, students, and welcome to our class today. We are going to begin a really fascinating journey into the world of metallurgy. You know, that's the science of how we get metals from the earth.
So, let's start with a simple question. Look around you. The chair you're sitting on, maybe a car outside, or even huge buildings, they all have strong, shiny metal. But where does it come from? How do we take a simple, dull rock from the ground and turn it into something so useful? Have you ever thought about that? Well, this amazing transformation, this is the magic of metallurgy that we are going to explore together today.
Okay, so here's our plan for today. We'll start by seeing where metals are found in nature. Then we'll look at something called the reactivity ladder, which is our guide. After that, we'll go step by step through how we extract the easy, the middle, and the toughest metals. And finally, we will see how to give them a final polish to make them pure. Ready? Let's begin. So our story has to start at the very beginning, right? Where do we even find these metals? Well, they're all around us, hidden deep inside the Earth's crust. But the thing is, you usually don't just find a big, shiny piece of iron or aluminum. No, they're often mixed up with other things.
Okay, so the first word we need to know is mineral. A mineral is basically any element or compound that you find naturally in the Earth's crust. Just think of the Earth's crust as a big box of different ingredients. All those ingredients are minerals.
But here's the catch. Just because a mineral has some metal in it, it doesn't mean we can use it. It's only useful if we can get the metal out easily and without spending too much money. And that's what we call an ore. So an ore is a very special kind of mineral. It's the one from which we can extract the metal profitably. Remember that word profitably. It's very important.
Now, when we dig an ore out of the ground, it's not perfectly clean. Of course not. It's going to be mixed with all sorts of unwanted stuff, like sand, soil, and little bits of rock. All of this unwanted material has a special name. We call it gangue. It's just like when you get vegetables from the market. You have to wash off all the mud and dirt before you can cook them, right? That mud and dirt, that's like the gangue.
Okay, so we have our ore and we've cleaned out the gangue. Now for the main part. How do we actually get the metal out? Do we use the same method for every single metal? The answer is no. So how do we decide? Well, we have a very special guide for this, something called the reactivity series of metals. Take a look at this chart. This is our guide, the reactivity series, or as I like to call it, the reactivity ladder. It's really simple. It just arranges all the metals based on how reactive they are. The metals at the top are super reactive, the ones in the middle are, well, medium reactive, and the ones at the bottom are not very reactive at all. And the method we choose for extraction depends completely on where the metal is on this ladder. It tells us the whole story.
So let's start our journey at the very bottom of the ladder. We'll begin with the easiest ones, the metals with low reactivity.
Now, these metals, like mercury and copper, are what we call lazy. They are not very reactive, so they don't form very strong bonds. This makes our job really easy. In fact, we can get the metal out from their ores just by heating them. That's it! Let's take an example. The ore of mercury is called cinnabar. Let's see what happens with it. Okay, now look at the reactions. Cinnabar is mercury sulfide, that's HGS. When we heat it strongly in air, the first thing that happens is that it turns into mercuric oxide, HGO. You can see that in the first equation. Now, we don't stop there. We just keep heating it, and because mercuric oxide is not very stable, it just breaks down, it decomposes, to give us pure, liquid mercury metal and oxygen gas. See? Just by heating, it's quite simple for these unreactive metals. All right, we've handled the bottom of the ladder. Now let's climb up a bit to the middle. This is where we find a lot of the common metals we use every day, like iron, zinc, and lead. Things get a little more interesting here. For these medium reactivity metals, just heating is not enough. We need a proper two-step process. Step 1 is to convert the ore into its metal oxide. Now you might ask, why? Why an oxide? Well, it's because it's much easier to get a metal from its oxide than from its sulfide or carbonate ore. So first we make the oxide. Then, step 2 is to reduce that metal oxide to get our pure metal. So, for step 1, converting the ore to an oxide, we have two different methods. And students, please pay close attention. These are very important keywords for your exams. The two methods are roasting and calcination. What's the difference? Roasting is done for sulfide ores, and we heat them strongly in excess air. See the example with zinc sulfide. But if we have a carbonate ore, we use calcination. Here, we heat the ore strongly, but in limited or no air. See the example with zinc calcinate. In both cases, see, we get zinc oxide. So, roasting for sulfide, calcination for carbonate.
Please remember this. Okay, so we've done step 1. We have our metal oxide, in this case, zinc oxide. Now for step 2, reduction. Reduction here simply means removing the oxygen. And how do we do that? We use something called a reducing agent. A very common and cheap reducing agent is carbon, which we get from Coke. So we heat the zinc oxide with carbon. What happens? The carbon is more reactive with the oxygen, so it literally snatches the oxygen away from the zinc, forming carbon monoxide. And what are we left with? Pure, beautiful zinc metal.
Now, carbon is a good reducing agent, but sometimes we can use another metal as a reducing agent. And when we do that, we can get some really powerful, really spectacular reactions. This leads us to a really fascinating question. Have you ever seen those huge railway tracks and wondered, if one breaks, how do they even fix it? How can you weld something so massive? Well, believe it or not, chemistry has the answer.
And here it is. This incredible reaction you see here is called the Thermit reaction. It's a type of displacement reaction, which we'll see in a moment. But the most important thing about it is that it's highly exothermic. That's a key word. It means it produces a tremendous amount of heat. So much heat, in fact, that it can be used to weld things like broken railway tracks or even cracked machine parts.
So let's look at the chemistry behind it. We take iron oxide, which is basically rust, and mix it with aluminium powder. Now, if you look at the reactivity series, you will see that aluminium is more reactive than iron. So, being the stronger, more reactive metal, aluminium will push the iron out of its place. It will displace it from the iron oxide. This reaction produces two things, aluminium oxide and pure iron. But look at the end of the equation, plus heat. So much heat is released that the iron, which is produced, isn't solid. It's in a molten liquid state. And this molten iron flows into the cracks and welds the pieces together. Isn't that amazing?
Okay, so we've covered the bottom and the middle of our ladder. Now it's time to climb all the way to the top. Here we find the kings of reactivity, metals like sodium, potassium, and aluminum. These are the toughest ones to extract, and they need a much more powerful method.
So, remember how we used carbon to snatch oxygen away from zinc? Well, that trick won't work here. Why? Because these metals at the top of the series, they love oxygen. They have a very strong affinity for oxygen. They hold on to it so tightly that poor carbon is not strong enough to pull it away. The bond is just too strong.
So, if carbon is not strong enough, what do we use? We need to bring in the ultimate force. We use electricity. This powerful process is called electrolytic reduction. The name tells you what it is. Electro means using electricity, and lytic means to break down. So we use electricity to break down the molten metal compound, for example, molten sodium chloride, to get our pure metal. So how does it work? Well, we have two electrodes, a negative one called the cathode, and a positive one called the anode. In molten sodium chloride, we have positive sodium ions, Na+, and negative chloride ions, Cl-. Now, opposites attract, right? So the positive sodium ions will move towards the negative cathode. When they reach the cathode, they gain an electron and become neutral, pure sodium metal. On the other side, the negative chloride ions travel to the positive anode. There, they lose their extra electrons and form chlorine gas. So we get our metal at the cathode. So there we have it. We have extracted our metal. Whether it was by simple heating, by reduction with carbon, or by electrolysis, our journey is almost over. But wait, the metal we get from these processes is still not 100% pure. It has some small impurities left. So we need one final step, a final polish, to get a truly pure metal.
And for this final purification, we again turn to our friend electricity. This process is called electrolytic refining. Let's take copper as an example. Look at the setup. We take a thick block of our impure copper and make it the positive anode. Then we take a very thin strip of pure copper and make it the negative cathode. And we put both of these into a solution of copper sulfate.
Now we pass an electric current through this setup. What happens is quite clever. Pure copper atoms from the impure anode dissolve into the solution, become copper ions, and then travel over to the pure cathode. When they reach the cathode, they deposit themselves there as pure copper metal. So slowly the impure anode gets thinner and the pure cathode gets thicker. And what about the impurities? Well, they are just left behind.
And those impurities that are left behind, they are insoluble. So they simply fall down and collect at the bottom, right below the anode. This collection of impurities has a special name. And again, students, this is an important keyword for your exams. It is called anode mud. It might sound like just mud, but sometimes it contains valuable metals like gold and silver.
Okay, so that was quite a journey.
from a simple rock to a pure metal. Let's just quickly recap the main idea. The entire process, the entire story of extraction, all depends on one thing, the metal's reactivity. For the low reactivity metals at the bottom of the ladder like copper and mercury, all we need to do is heat the ore. For the medium reactivity metals in the middle, like zinc and iron, it's a two-step process. First, roasting or calcination to get the oxide, and then reduction with carbon. And for the highly reactive metals at the top, like sodium and aluminum, carbon is no use. We must use the power of electrolysis. So, we have done it. We have our pure, shiny metal. But is our job done? Think about it. If you leave a piece of pure iron out in the rain, what happens? It starts to rust, right? So now that we've gone through all this trouble to get the pure metal, our next big challenge is to protect it. How do we stop it from getting damaged by the environment? This problem is called corrosion, and that is exactly what we will be exploring in our next session. Thank you, everyone.